you've asked you to identify the maximum of this over the interval, you can say 1 to 4. So x belongs to 1 to 4. So if you, this is a cubic polynomial, and what is this is, this is, if you denote it by g of x is equals to x minus 1 into x minus 2 into x minus 4. So if you open it up, it is x square minus 3x plus 2 times x minus 4. And if you further multiply, and what you will get is x cubed minus 7x square plus 14x minus 8. And you want to find the maximum over the interval x belongs to 1 to 4. So maximum certainly exists, right? Because this is a polynomial, it's a continuous function, and it is uniformly continuous on a closed interval. So the maximum will exist. So you are supposed to identify now the critical points. Okay. So for the critical points, what you need to get is, so you have to find x such that g dash of x is 0. Okay. So if you differentiate the cubic polynomial and you write the expression, it is 3x square minus 14x plus 14 is equal to 0. Okay, and this is a quadratic equation which you can solve, and which will give you the values. If you look, it is 14 plus minus square root of 14 square, that is 196, minus 4 into 3 to 14. So that is 12 into 14. So that is 168 divided by 6. So that is equals to 14 plus minus square root of 28 by 6. So if you use the calculator, what are the values are 3.2153. One value is 3.2153 and another value is 1.4514. Okay. And you have the other points are x equals to 1 and x equals to 4. The boundary points are also the critical points, right? Okay. So if you check all the values and in the magnitude sense, the function values, so you have to check g at 1, that is 0 equals to g at 4. Okay. And then you have to check g at 3.2153 in magnitude. Okay. What is the value? And magnitude of g of 1.4514. Okay. So replace, and then you take the maximum value. So if it is, let's say, the value is, let's say, is denoted by capital N. Okay. So I will just denote this capital N is maximum of this, comma this. Okay. And then the error bound is mod of E2. Error bound in quadratic polynomial, quadratic interpolation is given by less than equals to m3 by 3 factorial time n. So time n time m3 by 3 factorial. Okay. So let's do one application of this problem. Let's take this example. A table of values for f of x equals to cos x in the interval 0 to pi by 4 with the equally spaced data, okay, with equally spaced step size is to be constructed. To find the maximum step size, what you can choose size that can be used if the error in quadratic interpolation is to be less than 5 times 10 to the power minus 6. Right? So now in the earlier cases, what we have aware about the data. Okay, we were not given with the function, so we are not aware about the function, so that we cannot able to identify what is the estimate for m3 or m2 or and so on. The first derivative, second derivative, third derivative. Okay, so here we are aware about the function. Okay, and we are now try to identify the maximum step size, okay, which can be used, okay, with the specific tolerance. Okay, if that tolerance is less than 5 into 10 to the power minus 6, we require in quadratic interpolation, so we require the maximum step size we can use. So if you recall, the error was, if you recall, that is mod of E2 is less than equals to h cube by 9 root 3 m3. So if you recall, when the datas are equispaced, the error in interpolating polynomial that means where the interpolating polynomial is of degree 2. So we have estimated the following. So mod E2 is less than equals to this. So what is M3 was? M3 was maximum over x belongs to, you can say, x0 to xn. So x0 is the starting point, xn is the ending point. So A to B mod of f third derivative at x. Okay. So now since now you have f given function here. So given f is cos x. You know that if you take first derivative, it's minus sine, and the second derivative is again sine, cos or sine. So this will implies, so f third derivative for any x is certainly less than equals to 1. So we know this form. Okay. So what we can do further? So from here, using this implies mod of E2 error in quadratic interpolation is less than equals to h cube by 9 root 3 times m3, but m3 is less than equals to 1, so h cube by 9 root 3, and which we certainly wish to make it less than 5 into 10 to the power minus 6. So you are supposed to solve this inequality for h. So this implies h cube is less than 45 root 3 times 10 to the power minus 6. So this implies h is less than, so cube root of the right side that is going to be, if I give you the approximate number, if you use the calculator, that is 0.047947. Okay, so this will be, if you take the step size of maximum step size is 0.04, you can say this is 0.04, less than, strictly less than. So you can take 0.04 step size, then error will be less than 5 into 10 to the power minus 6 in quadratic interpolation. Okay, so this is an application. So similarly, you can go for the error in linear interpolation is to be less than 5 into 10 to the power minus 6. So that you can see, you can have the exercise that that you have find the maximum step size that can be used in the linear interpolation, so that the maximum error is less than 5 into 10 to the power minus. We want to give you the hint here. So if you recall, mod E1 was less than equals to h square by 8 times m2. And what is m2 was? M2 was the maximum of second order derivative over the interval. Okay, so maximum again less than equals to 1. So m2 is less than equals to 1. So that you can do now. Okay. Now we have seen two type of interpolating polynomials. Okay, so we have seen the form of two type of interpolating polynomial. One is Lagrange interpolating polynomial, and another was Newton interpolating polynomial. So Newton's form and Lagrange form. So two type of representation of interpolating polynomial we are aware about. Now, what is the disadvantage of Lagrange interpolation? Is you require to go for some tedious computations. Means like if you are given with the data x, x naught, x1, and so on, xn, and then y is let's say y naught, y1, and so on, yn. This is the given data to us. Okay, so for evaluating the Lagrange interpolating polynomial, you require to identify what are Li of x. And what was it is? This is product of I equals to 0, j equals to 0 to n, j not equals to I, x minus xj divided by xi minus xj. So 1 less than equals to 0 less than equals to I, less than equals to n. This product, if you have n number of data, you require to find this n number of multiplication for each term. Okay, so this is a tedious computation. Another drawback of Lagrange interpolating polynomial is, suppose you are going to add one more point here, let's say xn plus 1 and yn plus 1. So you are again going to identify Lix, derived cardinal function, which was obtained for the previous data, cannot be used for this new data if you are adding just only one point. Okay, it's not a recursive form. Okay, so you cannot use the previous variation. On the other hand, if you go for the Newton's interpolating polynomial, okay, so then you have already seen that if you use x naught to, let's say, xn minus 1 data, okay, and corresponding y naught to yn minus 1, for constructing an interpolating polynomial of degree at most Pn minus 1. So then if you add one more point here, let's say xn and yn, then you can certainly get Pn of x by using the previous one, by just adding a single term plus Cn. So Cn was obtained was the nth divided difference x naught to xn time product of I equals to 0 to n minus 1 x minus xi. Okay, so this is how, so the Newton interpolating polynomials are favorable many times due to this is its recursive nature. Okay, right. On the other hand, suppose your nodal points, so what is the advantage of Lagrange interpolating? Can we leave it? No. Okay, so there are some advantages of that Lagrange interpolating polynomials. The one of the major advantages, once you fix the nodal points, okay, once you fix this rule nodal points, so x0, x1, x2, xn means at these times, so 0 to you can say 30 seconds, we are noting down the different elements. Okay, so then there is no need to, so once you have obtained the cardinal functions, then you are not going to derive means additionally more now. Okay, that is now fixed. Okay, so once you have derived the cardinal functions, then we are simply, what is changing is y0 to yn, because at different time the experiment will give you some different results. Once if you first time experimented, second time experimented, and so on. So in that case, this Lagrange interpolating polynomial is more favorable. In that case, Lagrange interpolating polynomials are having the advantage over the Newton interpolating polynomial. Hope by given examples, okay, you have understood how to derive the divided difference table for a given data, and then write the corresponding Newton's interpolating polynomial. Okay, so let's see what will be the possible shape here. Okay, so means in Newton interpolating polynomial, do we have another type of error form? Yes. Okay, so that can be given. Okay, so let P be the polynomial of a degree at most n that interpolates a function f at a set of n plus 1 distinct nodes. If t is a point different from the nodes, so that already stated, then the f of t minus p of t is equals to the following. Okay, so this is what is error of f at t. Okay, so what we have learned is in n plus the previous theorem, error in interpolating polynomial, we have in the factor here, so we have seen the similar factor there. We have seen the similar factor there. Okay, and what we have seen in the product is the derivative, n plus 1 of derivative if you have used n plus 1 this n plus 1 nodal points. Okay, so now how to obtain this result? So this is very simple. If t is a point different from the nodes, then okay, so that how will you prove it? You have I wish to prove it. Okay, so p is the polynomial. P is an interpolating polynomial with degree at most n that interpolates a function f at a set of n plus 1 distinct nodes. So means p is, so p of xi is equals to f of xi 0 less than equals to I less than equals to n. So p is an interpolating polynomial, and p is an interpolating polynomial of degree at most n. Okay, now see, we have let t is distinct from x0 to xn. Okay, and then let q be an interpolating polynomial that interpolates f at x0, x1, and so on xn and t. Okay, so interpolating polynomial of degree at most n plus 1. So of degree at most n plus 1. So because you have n plus 2 points, so it's going to be interpolating polynomial of degree at most n plus 1. Now, since these are two interpolating polynomials, so Q is an interpolating polynomial of degree at most n plus 1, and P is an interpolating polynomial of degree at most n. So they are related because we have only added one more point. So by the similar construction, so what if you look up, if you follow the similar steps here, so then Q of T, or you can say Q of X, is equals to P of X plus, so P is an interpolating polynomial of degree at most n, and you are adding one more point. So plus the n plus 1th order divided difference, comma t, time product of I equals to 0 to n t minus xi. Now not that, okay, so not that q interpolates f at x0 to t. So not that q of t is equals to f of t. So evaluate this. So this is equals to, this is here is x minus x. So this is equation, if you say this is equation 1. So from 1 and 2. Okay. So from 1 and 2, we have, so replace x by t here. Okay, so q of x at t is q of t, p of x as t is p of t, and then this is this number, so t is a point, so this is already fixed number, so you only replace here is t. So what you will get is q of t is equals to p of t plus f of x0, x1, and so on xn comma t time. The product term is now was evaluated at x, now x previously, now it is evaluated at t. So at t fixed value, t minus xi. Now since q of t is p of f of t, so this will implies f of t minus p of t is equals to this f of x0 and so on x0, x1, and so on xn comma t time product of I equals to 0 to n t minus xi. So hence our result that, okay, so difference between, so at t, which is distinct from x0 to xn, so this difference can be obtained by this error in f at t can be obtained by the following expression. Okay, right. Now further, can we relate this divided differences by derivatives, since we are supposed to now estimate the derivative of f. Okay, because we have left out that, right, in error in linear interpolation, or error in quadratic interpolation, or error in n plus nth you can say nth degree polynomial, nth degree interpolating polynomial. So we have left out with mn plus 1. So capital Mn plus 1 we need to estimate now. So we need to get the approximation of this so that, so since many times you may not be aware about the function, but you can estimate approximately so that you can decide what will be the error in the given, error in the derived interpolating polynomial from the original function. Okay, right. So for doing so, you have the following result here, which says that the nth order divided difference is directly related with the nth derivative. So that will answer you. Okay, so if you have, so nth derivative may, so you will see in that table as well, divided differences table, that so after some column like first divided difference or second divided difference, further divided differences are 0. Okay, so let's have the following data now. This exercise here, one exercise. So I wish to construct the interpolating polynomial which fits the following data. So I am writing directly in the vertical form. So x, f, so minus 2, 0, 1, 4, 5. And value of f at those nodal points are 9, 1, 6, 57, and 86. So by looking at the data, what you can make the observation that there are 5 number of points. So there are 1, 2, 3, 4, 5 number of points. So n plus 1 is 5, right? So it will be 4 degree polynomial. So interpolating polynomial is going to be a polynomial of degree 4. But it will not be the case when you going to derive originally. So if you go for first divided difference, so I'm going to derive the first divided difference. So I'm going to use this. So 1 minus 9 divided by 0 minus 2. So that is this is plus 2. That is minus 4. So this is 5. 6 minus 1 by 1 minus 0. That is 5. If you go for next is 57 minus 6 is 51 by 3. 4 minus 1 is 3, so that is 17. And if you go for this, that is going to be 86 minus 57 is 20, right? 29. 29 by 1, that is 29. So now if you go for second divided difference, so that is going to be 5 minus 4. So this is minus 4 divided by 1 minus 2. Right? We are skipping 1 in between. So 1 minus 2 is 3. So 5 plus 4 is 9 by 3 is 3. So if you go for the second entry here, 17 minus 5 is 12. Divided by 4 minus 0. That is 4. That is 3. Now the next is, this is 29 minus 17 is 12. Divided by 5 minus 1. That is 4. That is 3. And now if you see in, here onwards, so third divided difference. Third divided difference is, you are going to use these two and use these two. 3 minus 3 is 0. 3 minus 3 is 0. And if you go for fourth one, so that is going to be used, this 0 minus 0 is 0. So the divided difference table tell you directly that the interpolating polynomial is of degree 2. Okay, is of degree 2. So this is your C naught, right? This is your C naught, or first 0th divided difference, first divided difference, second divided difference, third divided difference, fourth divided difference. So by looking at the divided difference table, you can actually tell what will be the possible degree of interpolating polynomial. So at most, you know, that is at most is 4, less than equals to 4. So what will be the exactly here is second degree polynomial. Okay, so see, okay, so this is what the advantage of again Newton's method, Newton's interpolating polynomial. Okay, on the other hand, if you go for the Lagrange form of interpolating polynomial, then you are supposed to identify all the possible cardinal functions using these nodal points, means L01, L0x, L1x, L2x, L3x, and L4x. That is a tedious job. And then again put a linear combinations of in the form of y naught plus, so you have the linear combination of summation yj Lj of x. So j is equals to 0 to n. Then it will cancel out the things and it will turn out to be second degree polynomial. On the other hand, if you see this, here, look at the divided difference table. This is how it is easy for deciding the degree of the polynomial and writing straightforward the interpolating polynomial. So that is what the advantage of, again, in Newton more advantage of linear interpolating polynomial of Newton's form. Okay, right. Okay, so here why it is happening is this is going to be turned out as a second degree polynomial, so whose third derivative is 0, third divided difference is 0, fourth divided difference is also 0, fourth derivative is also 0. So can we relate them? Yes. So this is what the result says. If f is n time continuously differentiable, means you can perform a derivative of a given function f n time, okay, at pace. And if you have the x0 to xn are distinct points in AB, then there exists a point z in AB such that this happens. Okay, so how would you show this? Okay, so this is very simple here. So we are going to use the result error in polynomial interpolation, and then the result what we have derived now, it is error in Newton interpolation. So we are going to use that result to establish this. Okay, so proof of theorem, you can say proof of you can theorem that the theorem. The proof of that theorem can be understood like this. Okay, so let P be the interpolating polynomial, the interpolating polynomial of degree at most n minus 1. At most n minus 1 that interpolates f at x naught, x1, and so on xn minus 1. So we have left out for the time being xn point. Okay, right. So then what we have is p of xi is equals to f of xi for 0 less than equals to I less than equals to n minus 1. Then error in polynomial interpolation, what it tells is then for every x in upper interval AB, that is x naught to xn minus 1, you can say. So that is your A and that is your B. If you recall the interpolating polynomial theorem, there exists a z which is depends on x in x naught to xn minus 1 such that you have f of x minus p of x is equals to f nth derivative at that z divided by n factorial time product of I equals to 0 to n minus 1 x minus xi. So earlier you had the n plus 1 points. Now you have taken the n points. So you are having nth derivative here. So you have the nth derivative here. That is. Now we are going to use the previous result. So means because we are only adding a point x equal to xn. So from here, if you this you can say this is equation 1. Okay. So from equation 1 gives what it gives you f of xn minus p of xn at x equals to xn, which is distinct from x naught to xn minus 1. Okay, so see, we don't have any order here. Okay, so we have not said that x naught to xn are in order form. So xn you can means you can shift between two x naught to xn minus 1. So that this condition should meet that x belongs to x naught to xn minus 1, because the result holds only for that. So keep in that mind. So that xn, so these are in our hands, so that it can be done. So the next point, xn is in between of them. So xn one gives that is equals to f nth derivative at z by n factorial time product of I equals to 0 to n minus 1 time xn minus xi. Okay. So xn is, so this is already given that xn is distinct from x naught to xn minus 1. So this product will never be 0. Okay. Right. Also, if you apply the previous result, also we have f of xn minus p of xn. If you recall that f of t minus p of t, that is equals to f of x naught to xn minus 1 comma t. So t is here xn time product of I equals to 0 to n minus 1. So t minus xi. So t here is xn minus xi. So this is, you can say this is 2, this is 3. So from 2 and 3 you have the result. So from 2 and 3 we have f of x naught to xn is equals to f nth derivative at z by n factorial. Okay, right. Okay, so now we are going to move for defining Newton's forward interpolation and backward interpolation formulas. Okay, means we are going to see now in see more simple form of Newton's interpolating polynomial. So okay, so that means we are going now to particular case where the data whichever has been given is equally spaced. Okay, is equally spaced. Okay, so we are going to assume equispaced data. Okay, so we are going for now, we can say equispaced data is given. Okay, so let's say the step size is h. So step size is h. So the data is, instead of x naught, x1, x2, xn, what is there is x naught plus h, x naught plus 2h, x naught plus 3h, and so on, x naught plus nh. Means these xi's are related. If you know the step size, you can and x naught. If you know h step size and x naught, then you have the formula for getting xi, that is x naught plus ih. So where I is running from 0, 1, 2, and so on till n. Okay, so we are going to now define Newton's interpolating polynomial, means forward by using forward difference, backward difference. Okay, and we are going to use one more very special type of difference operator known as central difference operator. So why we are going to forward this with this is because we are going to get good estimate for the derivative of the function by using the data. Okay, so the only data is if the only data is known and function is not known, still you can estimate their derivative. Okay, so we are going to now, you can say, define some of the operators which are called finite difference operators. So finite differences, or you can say finite differences or finite difference operators. So they are very important. Okay, so the very first operator is what we are going to define is shift operator. So this is a very important operator which actually shift to the next value. So that is clear by the name, means name itself, shift. Shift is shifting. Okay, so which we denote it by E, which act on f at x, and which if you give the input f at x, it will give you the output f at x plus h. So h is mass spacing. Okay, h is step size. Okay, so this is e f of x is f of x plus h. So from here, if you apply again e here, so e, you apply one more time e to f of x, means that is equals to e applied on f of x plus h, that is equals to f of x plus h plus h, so that's plus 2h. So if you do you are two time applying e on f, it will give you the second step, means two time forward. Okay, so one forward here is two forward here, two steps it has taken. Okay, so in general, if you apply e and so on f k times, which we are going to denote it by e to the power k, then the output is you have taken k steps from x, so x plus kh. So this k could be, so where k is any positive integer, negative integer. It is also possible by taking h equals to minus h. So that also can be e power minus k f of x is f of x minus kh. So integer and any fraction, any fractional number, fraction, or means you can say rational number, any rational number. Means e to the power half f of x is defined by f of x plus h by 2. E to the power 3 by 2 f of x is defined by f of x plus 3h by 2. So this is how the shifting operator is done. And if you look at the minus case elsewhere, so e to the power minus half f of x is shifting is previous value with the half step. So x minus h by 2. E to the power minus 3 f of x is equals to f of x minus 3h. So this operator behaves like this. Okay, right. The second operator we are going to define, then we will identify the relations also. Okay, the next operator is forward difference operator. Forward difference operator, which we are denote by this delta. So, which is defined as delta f of x. So, as the name is suggesting you forward, you go forward and take the difference from the previous value, the present value, you can say. So, that is equals to f of x plus h minus f of x. So, future minus present. So, that will define the forward difference operator. And that you can also show that this is a linear operator. Okay, delta of a plus b f of x, you can f of x plus g of x. Okay, so you can show that delta is linear operator. Okay, if you wish to recall what is the linear definition, is delta of a f plus b g of x is equals to a times delta f of x plus b times delta g of x. Okay, so that you can show very easily like a derivative. Okay, and so this implies, so if you go for delta square, means if you apply delta 2 times, means delta over delta f, what you will get is delta of f of x plus h minus f of x. Since delta is linear, so that is equals to delta f of x plus h minus delta f of x. So that is equals to, so the next value of f of x plus h is f at x plus 2h minus the present value, that is f of x plus h, minus delta fx is f of x plus h minus f of x. So that is equals to f of x plus 2h minus f of x plus h minus f of x plus h is minus 2 times f of x plus h minus minus plus f of x. And what we are going to do is now delta acting over on delta. Okay, so 2 times acting, so that we denote it by delta square. So if it is acting k times, so it is delta to the power k. Okay, so similarly, so what you have is delta square f of x, delta acting over delta, that we are denoting by delta square, that is equals to f of x plus 2h minus 2 times f of x plus h minus f of x. Now, then we are going to go for delta cube. Means one more time delta is acting. So this is enough to take the forward difference of this. Okay, so and use the linearity. So that is equals to delta of f of x plus 2h minus 2 times delta f of x plus h minus delta f of x, and then you apply the definition. So that is f of x plus 3h minus f of x plus 2h minus 2 times, so this is for first one, minus 2 times f of x plus 2h minus f of x plus h minus Delta fx is f of x plus h minus f of x. Now, what is if it is right in the simple form? F of x plus 3h. Now, f of x plus 2h with the negative sign, minus here and minus 2. So that is equals to minus 3 f of x plus 2h. Now, minus 2 into minus is plus 2 f of x plus h. Right? Time here is this was plus here. Right? This was plus. So if this is minus plus 2 times f of x plus h and plus 1 time f of x plus h. So plus 3 times f of x plus h minus f of x. Now I will stop in a minute. Okay. So if you look at this carefully, so the coefficients here, f of x plus 2h is f of x plus h, and this here, and we have to see the coefficients of these here. The very first thing is, if you have the second order divided difference, second order power difference, you can say, you have the positive sign f of x. If you have third, you have the negative sign with f of x. If you have first forward difference, you have the negative f of x. Okay, right. One more important thing is the coefficients are in the square. It is, if you recall, this is 2c0, 2c1, this is 2c2, the binomial coefficients. Similarly here, this is 3c0, this is 3c1, alternative plus minus 3c2, and that is 3c3. So we will generalize this again in the next session. Okay, we will generalize this result in the next session. Okay, in terms of binomial coefficients and relate it with the shift operator. Okay, right. Okay, then here is we are stopping our this lecture session.